on number 3. So in number 3, it asks us to calculate the net torque about the point 0, which is this point right here. For the two force applied and the weight of the rod. The rod has a mass of 1.5 kilograms. Calculate the angular acceleration of the rod. Okay, so they kind of have an incomplete free body diagram here for us, including angles. We can assume that this angle is going at a 90-degree angle here, which is fine. And we also have the weight of the rod. The rod is a uniform rod, I believe, so, and we can also see here that it is 5 meters long. So right about at 2.5 meters. The center of mass of this object will be pulling downwards with its mg force. So we'll also include that in the calculation. So we're looking for what is the net torque. So we're looking at sigma tau. And if we label these things here, we have sigma tau, tau 1. We have tau 2 and tau 3. We're calling this one torque 3 down here. And we have to keep in mind that torques have directions just like forces do. And it's customary to label torques that are pulling clockwise, so in this direction, as positive. So our torque 1, that will be positive. F2, that is pulling against, it's pulling counterclockwise, so this one's going to be negative. And then the weight is pulling in the positive direction as well, so that will also be positive. All right. So from here, we're going to use our definition of torque to kind of break these things down. So flashing back to the notes here, we're going to use this equation here where we have torque equals Rf sine phi, where phi is the angle between our R vector and our F vector. So looking here, we have sigma tau. Nothing happens on that side. T1, we're looking at a radius of 5 meters, a force of 8 newtons, and a sine of our phi, which would just be 90 here. Okay. Torque 2. This time we have a radius of 2, because it's attached at a different location on the rod. Our force is 22 newtons strong. And we have a sine of 30, because that is the angle between our R and our F. And then finally, for our weight force, we have a radius of 2.5, because it's halfway through the rod. The mass of our rod is 1.5 as given up here, and our G value is 9.8, and then we have a sine 90 for the direction. So for this part, all we really need to do is just evaluate this, and that should do the trick for letter A. So let's add all this business together. So we have 5 times 8 times sine 90 minus 2 times 22, 2 times 22, sine 30, plus 2.5 times 1.5 times 9.8 times sine 90. And we wind up with a net torque of 54.75 newton meters. Now, letter B asks us to find the angular acceleration of the rod. To do that, we want to use the net force equation but the angular net force equation to do that. So let's pull that up here in a second. So we're looking at this equation here. So we want to use sigma tau equals I alpha. Looking for alpha, we know sigma tau, but we need to figure out what I is. So let's take a look back in our I section here. When we're looking for the moment of inertia of a object, we can use some of these shorthand equations to get us through that. We are looking at a long rod, but our axis is at the end, so we want to use this equation here. So our I, our moment of inertia for our rod, will be 1/3 ml squared. So if we plug in at 1/3, 1.5 kilograms is our mass, and our length is 5. So plugging that in real fast, 1.5 times 5 squared, we get a moment of inertia of 12.5. And those units are kilograms meters squared. And now that we have that, we're ready to go over here and solve. So plugging in our net torque was 54.75. Our moment of inertia is 12.5. And alpha is unknown. So dividing 54.75 by our moment of inertia should give us an angular acceleration of 4.38 radians per second squared. So this rod will swing down that direction, swing down in the the clockwise direction. Number 4. Number 4 is very much like a Newton's second law kind of situation, back from Unit 4, but once again we're adding the angles to it, so it makes things a little bit more complicated. So here we have a grinding wheel. It has it's a uniform cylinder with a radius of 8.5 centimeters, so I'm just going to put R equals 0.085 meters, and a mass of 0.55 kilograms. In letter A, it asks us first to determine its moment of inertia about its center. So in letter A, we are trying to solve this for I. Now, fortunately, once again, we have our little handy equations for I. And since we're looking at a cylinder through the with an axis through the center, we're looking at 1/2 mr squared as our equation. So I should be 1/2 mr squared. So plugging into this, we have I equals 1/2 times our mass, 0.55, times 0.085 squared. And plugging that in, we get I equals 0.00199 kilograms meters squared. Or if we want to write it in scientific notation, because this thing's a little bit small, 1.99 times 10 to the 3 kilograms meters squared. Those will both be fine, depending on whether you prefer scientific notation or the weirdness going on there. All right, letter B then asks us, this is where the problem gets a bit more meaty. The problem asks us to figure out the applied torque needed to accelerate it from rest to 1,500 rotations per minute in 5 seconds, if it is known to slow down from 1,500 rotations per minute to rest in 55 seconds. So this scenario is kind of giving us a bit of an odd thing going on. So let's kind of think about what's going on. We know that we are going to have some kind of net torque in this situation. They are asking us to find the applied torque. So whatever the machine is doing to get it up to speed. But if it is up to speed and let go, it does come to rest after some time. So that does mean that whatever torque applied that we do put onto this thing, we are going to also experience some friction torque. So that'll be some like rotational or spinning friction or rotating friction in the grindstone that'll eventually slow it down. So to be able to get it up to speed, we have to overcome this friction force piece here as well. Let's take care of our first thing here, and let's take this 1500 rotations per minute, and let's convert that into radians per second, because that's just not a easy unit to work in when we're talking about physics. So let's get out of the rotations first. So for every one rotation, we go through 2 pi radians. That should take out the R part. And we want to get out of minutes. Technically, the minutes is sitting down here, so rotations per minute. The minutes will need to cancel. We have 1 minute on top, 60 seconds on the bottom. So that should give us the amount of radians per second that this thing needs to travel to get up to speed. So I'm going to multiply by 2 pi and divide by 60. And we figure out that the rotations per second should be 157.08 radians per second. So that number will be important for us. All right, so we need to kind of figure out a couple things here. But maybe let's take a look at the friction torque first. So let's try and find torque friction first. So if we were going to try and find this, we know that the torque friction must be equal to the I times the alpha. Now we already have I. Alpha is a different story, so we need to kind of go and figure out that alpha for the situation. Fortunately, we do have an equation for that. So since we know that the angular speed now, that's omega. In this situation, omega naught would be it at full speed already. Omega would just be 0 because it's coming to a stop. And the time element, they tell us it takes 55 seconds for it to come to a stop. So we want to try and find this alpha. We know this equation. We've used it before in this problem set. Omega equals omega naught plus alpha t. And if I plug in my stuff, we get omega equals, oh, I know this is 0, silly, 157.08 plus alpha times 55. So if I subtract that over, I get 157.08 equals 55 alpha. And dividing both sides by 55, I get negative 2.86 radians per second squared as the alpha in this situation. And if I plug all this business in over here, I get 1.99 times 10 to the third for our I value, and negative 2.86. And this torque winds up being a small number, but we get negative 5.69 times 10 to the negative third newtons meters. All right, we're going to finish this one up in the next video.